Welcome to Multivariate Calculus. Today we are going to explore one of the most beautiful and powerful ideas in mathematics, the Gauss Divergence Theorem. This theorem gives us a magical way to connect what happens on the outside of an object to what is happening deep inside it. Let us dive in and see how it works. Imagine a crowded room where people are leaving through the doors. If you want to know how many people left, you have two choices. You can stand at the doors and count every single person walking out. Alternatively, you can look at the whole room and count how much the total population inside decreased. Both methods must give you the exact same number because people do not just vanish into thin air. This is exactly what the Gauss Divergence Theorem does. But instead of people, we track the flow of fluids or energy. Before we state the theorem, let us define a few key terms. A vector field is a space where every point has an arrow showing a direction and strength, like wind speeds. Flux is the total amount of that wind actually pushing through a specific surface. Divergence is a mathematical measurement of how much a specific point acts like a source pushing fluid out or a sink sucking it in. Finally, a closed surface is a boundary with no holes that completely traps a 3D space inside it, exactly like an unbroken eggshell. Now we can state the theorem mathematically. The Gauss divergence theorem states that the total outward flux of a vector field across a closed surface is perfectly equal to the volume integral of the divergence of that field over the enclosed region. On the left, we have the surface integral, calculating the flux pushing out. On the right, the volume integral adds up the divergence across every tiny piece of the volume. If the divergence inside increases, meaning more fluid is created, the outward flux on the left must increase by the exact same amount to balance the equation. Let us look at this visually. The diagram summarizes the entire theorem. The small red arrows inside represent the divergence at individual points within the volume. They are the microscopic sources generating flow. The large black arrows piercing the outer skin represent the total flux escaping the shape. The theorem guarantees that adding up all the small internal arrows gives you the exact same mathematical result as measuring the large external arrows. It is a perfect balance between the inside and the outside. Before we move on, let us see this with a concrete example. We want to find the outward flux of a vector field across the surface of a sphere with radius e. Calculating the surface integral directly would require complex spherical parametrization. Instead, we use the theorem to convert it into a simpler volume integral. First, we find the divergence of the vector field. We take the partial derivative of each component with respect to its own variable. Adding these together, we get a constant divergence of 3 everywhere in space. Continuing with our sphere, we now set up the volume integral. Because the divergence is a constant number, 3, we can pull it out to the front of the integral. The remaining integral is simply the geometric volume of the sphere. We do not even need calculus here. We just substitute the standard formula for the volume of a sphere, which is 4/3 pi times the radius cubed. The 3's cancel out, leaving us with our final answer. The positive result physically means that more stuff is leaving the sphere than entering it. Let us look at a slightly more complex example. We need to calculate the total flux out of a closed cubic box. A cube has 6 separate flat faces, so calculating the surface integral directly would require solving 6 different integrals. The theorem allows us to bypass that nightmare. We begin by calculating the divergence of the given field. We differentiate each component and add them together. Unlike the previous example, the divergence here is not a plain constant. It depends on the height z. As we move higher up in the box, the field expands more rapidly. Now we place this divergence into our triple integral, using the boundaries of the cube, from 0 to 1 for all 3 variables. We will integrate from the inside out, starting with the variable x. The expression inside does not contain an x, so it acts like a constant. Integrating with respect to x simply attaches an x to our expression. Evaluating this from 0 to 1 just multiplies the expression by 1, leaving it completely unchanged. We are now ready to integrate with respect to the remaining variables. Continuing our calculation, we do the exact same thing for the variable y, which again just multiplies the expression by 1. We are left with a simple single integral with respect to z. This represents adding up the horizontal slices of the cube from the bottom to the top. We use the power rule for integration to find the antiderivative. Finally, we substitute our upper limit of 1 and lower limit of 0 into the variables. The final flux is 6. This means 6 units of the vector field are pushing out of the cube's 6 faces combined. Now that we have used this formula, let us understand where it comes from conceptually. We will prove this theorem for a simple 3D rectangular box to see exactly why the math works out so perfectly. We assume our vector field has 3 distinct components, which we will call P, Q, and R, representing the flow in each direction in space. By breaking the problem down into these individual directions, the complex math becomes much easier to handle. We will focus on just one direction first, the vertical flow moving up and down along the z-axis. We set up a triple integral to add up the vertical divergence throughout the entire volume of the box. This is our starting point. Let us evaluate that vertical divergence we just set up. When we perform the innermost integration with respect to the variable z, the fundamental theorem of calculus gives us a beautiful and powerful mathematical shortcut. Integrating a derivative simply gives us the original function evaluated at the upper and lower boundaries. So we get the vertical flow at the top boundary minus the vertical flow at the bottom boundary. This resulting double integral is exactly the mathematical definition of the flux passing through the top and bottom surfaces of our box. We have successfully linked the internal vertical divergence to the external vertical flux for this specific direction. To complete the proof, we simply repeat this exact same logical process for the horizontal x direction and the depth y direction. This gives us the flux through the remaining 4 sides of the box. When we add the results from all 3 directions together, we get the total flux through all 6 faces of the box on one side of the equation and the total 3-dimensional divergence on the other side. This proves that the total internal divergence perfectly equals the total surface flux, giving us our final theorem. The logic holds for any complex shape because you can always build any 3D volume out of millions of these tiny microscopic boxes. So we have proven that the theorem holds. This brings us to why it matters in the real world. The Gauss Divergence Theorem is not just a clever math trick. It is the absolute foundation of modern physics and engineering. In electromagnetism, it forms Gauss's law, explaining how electric charges create electric fields. In fluid dynamics, it guarantees that water flowing through a pipe does not magically disappear. In heat transfer, it helps engineers calculate how quickly a hot engine block will cool down. Without this theorem, designing electric motors or predicting the weather would be mathematically impossible. Let us summarize what we have learned. The Gauss Divergence Theorem is a powerful bridge between 2 different ways of looking at the world. It proves that measuring the flow across the boundary of a shape is mathematically identical to measuring the sources of that flow inside the shape. Practically, whenever a surface integral seems too difficult to solve, this theorem offers an escape route by turning it into a manageable volume integral. You have now mastered a concept that unlocks the ability to solve complex real-world physics problems with ease. Great job!